Good afternoon, friends. Welcome back to another domain analytics session from 360DigiTMG. So far, we have covered e-commerce, as you all know. And in e-commerce, we have covered different models, different pre-processing techniques, and all of those things. And we have started taking a look at supervised learning. Now, if you remember, supervised learning is where we have supervised learning is where we know the output variable. Okay, we know what output variable is present. So for example, if you're trying to predict sales for a company, you would know the sales, you would know how much sales there are. Okay, that is what that is what regression, that is what supervised learning is. Okay, so y is our output, and we know what y is. Okay, and if you know y, then you will also know various what are the various x's. X would be the inputs. So essentially what you're trying to do is you're trying to find y's relation with x. Okay, how changes in x affect y. Okay, so yesterday we had seen knn, k nearest neighbor. Now in knn we had seen that we can use knn for both regression and classification. Okay, so what happens in classification? This y is categorical. That means y is a non-numerical value. Let's say we are working on customer churn and we are focusing on two. Will they come back or will they not come back? When they will not come back, that means we can say that the customer will leave. So we might have a whole bunch of factors that can affect their churn, and based on those factors we make some decisions. Okay, we make some predictions. All right, so that is the whole point of classification. Similarly, you will have something called regression. Now what happens in regression? Y is numeric, or you can say y is continuous. Okay, so you have a numerical output now. Now let's say you're trying to predict profit. Now profit can't be yeses or no's, right? Maybe you have a scenario where you're trying to predict if you'll make a profit on the sale or not, but normally profit would be some numeric value. Okay, it would be some numeric value. All right, so what happens here? Here what we'll try to do is we'll try to again define some equation, define some relationship between the profit as well as the various inputs, how those inputs affect our model. Okay, so that is the basic. Okay, so today we'll be covering linear regression. Linear regression is simple linear regression. That means you're trying to create a linear relation between the columns. Okay, so let's just see. So Okay. So what can we do here? So let's say in linear regression, we have a few terminologies that you need to be familiar with. Okay. So what are these terminologies? You have the dependent variable. Now, what is the dependent variable? This is your target variable. This is what we call the output. Okay. So this is the variable you want to predict. For example, we had profit. So in this scenario, profit would be a dependent variable. Okay. So this is what we call as the target variable or y. This is our y. Okay. And then we have the independent variable. These are the variables that affect the dependent variable or the target variable. Okay. So this will be our inputs or x. Okay. So then you have outliers. Outliers would be anomalies within a data set. Anomalies are unexpected values. Okay. And then we have a very important concept that we call as multicollinearity. Now, what is multicollinearity? It means when these independent variables, these x variables are highly collinear to each other, are highly correlated to each other. Now, correlation, first we'll understand correlation after this. Okay. This is called collinearity and this should not be present in the data. You have to remember this, collinearity should not be present in the data. Okay. So what is correlation? Correlation is relationship of one variable with another. All right. So correlation is defined within this range, -1 to 1. Okay. If you have -1, there is perfect negative correlation. Now what this means is if you have two variables x and y, when the value of x increases, the value of y decreases with the same magnitude. And if you have one, that is perfect positive correlation. All right. So value of x increases, the value of y also increases. Okay. So graphically, This is what it would look something like this. Okay. So this would be negative. This would be positive correlation. Okay. So you want your correlation. There should be some sort of correlation, but it should not be very high correlation. You don't want all your columns to be highly correlated to each other, because then it becomes difficult to analyze what is affecting the output, what is affecting the model. And when it becomes difficult to analyze that, then your regression becomes pointless. Okay. So we have to know the concept here of multicollinearity. And then we have underfitting. What is underfitting? Underfitting is when your algorithm is performing poorly on training data. The data you're training it is performing poorly on that. That is what we call underfitting. That means your algorithm is not even doing its basic task properly. Okay. Similarly, you have overfitting, where your model is performing well on training data. That means your training data is good, giving good accuracy, but test data is poor. Okay. So that is overfitting. So you'll come across these scenarios a lot. Okay. So we have to learn how to deal with them. Okay. All right. So why do we use regression? Regression is useful because it estimates the relationship between the target and the independent variables. It creates an estimate of the relationship of all these variables that are present in the data. It is useful for finding trends. What sort of trends are there? What sort of, you know, if you have some trend, if you have some prediction, if you are predicting some peaks and all those things, you can do it using regression. Okay. It can also help us determine the most important factors that affect our output, as well as the least important factors. And at the same time, it can help us, you know, find how factors impact each other. All the factors, what they do for each other. So that is what we can find. Now, in regression, you will come across multiple formats. You'll have linear regression. Linear means a simple line regression. Then you'll have logarithmic regression. That means you're taking the log. Okay. So you'll have linear regression, you have log regression. And then you will have polynomial regression. You will have ridge and lasso regression. So you have a bunch of different regression techniques. There are more techniques you can see. If you are curious, you can obviously always Google and find out. So these are the different regression techniques we have. Okay. So today we'll be covering linear regression. Okay. Now linear regression, as the name suggests, means line. Linear, what is the meaning of the word linear? Linear means line. Okay. So what are we doing in linear regression? We are trying to create a line, an equation line that is passing through the input and the output variables, and it is defining the relationship between those variables as close to the actual output as possible. Okay. So we use this for predictive analysis. Now, what does this mean? This means we are trying to make some predictions. We are trying to do some predictions. Again, we have learned so far that the whole point of ML models is to make these predictions. So that is exactly what we are doing here. We are taking some ML model and we are making the predictions. Okay. So linear regression is one of the many ways in which you can do prediction. Okay. And again, it is easy to work with. Generally, you will find that regression models are rather easy to work with compared to other models like neural networks. Regression models is something that you can work on an easier manner. Okay. And it shows the relationship between continuous variables. All right, whatever continuous variables there are, it will show the relationship between them. Okay. And again, it is used for obviously regression problems. So these are some basic common things, right? The basic common things like you have some continuous variables in your data set. Now, if you are curious about finding the relationship between each of those variables, what do? You do linear regression, right? You can do other regression techniques as well. Okay. And it shows the linear relationship. What sort of linear relationship? What sort of relationship it is showing? It is showing linear relationship between X, your independent variable, and Y, your dependent variable. All right. So if you have one X and one Y, we call it simple linear regression. One here. And if you have multiple X and Y would be one. Obviously, you would have a single output. You cannot have multiple outputs, right? That goes against the purpose of this model. What can you do if you have multiple outputs, right? So this is multiple linear regression. Simple enough to understand, right? If you have one input variable, it is simple linear regression. If you have multiple input variables, it is multiple linear regression. Now the equation here is y equals to a of x plus b. Okay. Now what is y? Y is your dependent variable. Okay. And x is your independent variable. A is some linear coefficient. And b is the slope intercept of that variable. And this is the equation for simple linear regression. How is it the equation for simple linear regression? Because we have a single x and a single y. We don't have multiple x's or multiple y's. Okay. So how would we know if there are multiple what do we do when you have multiple x's? So you'll have y equals to a x1 plus b x2 so on until x of n plus some constant. C stands for this constant value, that is the intercept. So here again x1 x2 would be your independent variables and y1 y2 would be your sorry abc, they would be your linear coefficients. Okay, so that is linear regression. All right, so moving forward, we also have logistic regression. This is used for classification problems. Okay, logistic regression is what we use for classification problems. Why? Because it can work with discrete values. Okay, so that is where logistic regression comes in. You can have binary discrete values, you can have multi-discrete values, or you can have ordinal values. So it can do excuse me, it can do any of those. All right. So that should cover the theory. Let me just quickly check if we have anything else we can add. Okay. So now let's look at some practical implementation of linear regression. So again, Let's understand the libraries we'll be using. NumPy, Pandas, standard. Matplotlib, standard. Cvon, standard. sklearn, from sklearn, we are taking the train test split. Now, this is another important factor here. In, excuse me. In unsupervised, we don't split the data into test and train. We don't do that. Remember that, no splitting. We just take the entire data and we figure out the patterns. But in supervised, we first train the ML models. Okay. And then finally, the last step would be test prediction. All right. And then we compare it with the original result. Okay. And then we have linear regression. So from sklearn, we can directly import linear regression model. Of course, you can also use stats model. So stats model also has a regression model. Okay, so we'll take a look at that as well. All right. Okay, so let's import all the libraries. Let's import our data. So we don't have any null values in this data. Now let's understand the data. So we have the email address of a customer. We have their actual address. We have their avatar. What avatar they had on their profile. Avatar means what sort of color they had on their profile. And then we had what is the average session length, time spent on app, time spent on website, their length of membership in years, and how much money they are spending every year. Okay, so again, we are trying to predict the spend, how much money they will be spending. Okay, so let's draw a pair plot. So you can notice, you might notice that length of membership and yearly amount spent, there is some sort of direct relation, right? Right? Do you notice that? You're noticing it, right? Similarly, compare it to the other pairs. This one has some relation, and this one, time on app, some relation, not the clearest as length of membership, but there is some sort of linear relation. Okay, you might notice that as the length of membership increases, the yearly spent amount is definitely increasing. Okay, and similarly here, as the time on app is increasing, there is a positive trend. But for example, let's look at this time on website compared to yearly spent. It's a random pattern. There is no single pattern. Okay. And then again, average session length, some pattern is there, even if the pattern is not as strong as these two. Okay. So using this pair plot, we are able to observe some changes in the data, some relationship between the data. And to confirm it, we'll draw a box plot, sorry, a correlation plot. Now, you notice something. Length of membership and time on app have 0.81 and 0.5 correlation. We can call this good correlation. It is not high, but it is good. Okay. And length, average session length is poor correlation. Okay. But there is some correlation that exists. And time on website is a negative, barely any correlation. So we'll ignore time on website altogether. Okay. So now we can simply start working on our model. So what we'll do here is first we'll what should we do here? Okay, so what we'll do here is first we'll build a simple linear regression model. Okay, so we'll take X as customers, the name of our data frame, and then we'll just take length of membership. And Y will take as customers, yearly amount spent. So we are taking the column that has given us the highest degree of collinearity and we have taken it. So we have this X and simply we can also check Y. All right. So we have this. Now we'll just take this train test split. We'll split our data in train and test. And then we'll build a linear regression model. We'll say LM equals to linear regression. And then we want LM dot fit. We want to fit it on the train data, obviously. So we'll fit on the train data. So it will return us a linear regression model. Okay. And then we'll quickly check for the coefficient as well as the intercept value. Okay. So there will not be any time on app. And there will be only a single coefficient value. Okay. So this is what it looks like. Now, what this means here, how do we make sense of it? We know X as length of membership. So what would this look like? Y would equals to 64.293 of X plus 272.46. So this would be our Y. Now, if I want to predict for 1.5 months, what I will do here is Y equals to 64 times 1.5 plus 272. Okay, this would become what? 96. 96 plus 272 becomes 28. So this becomes Y equals to 368. So we are saying that if we are only considering the length of membership, a person who has got a membership for 1.5 years is likely to spend 368 annually. So this is simple linear regression because you have one X and you have one Y. So now we'll take this data and now we'll fit it on our test data. Okay. So now we'll see. Now you can see the predictions. Okay. You can see that the actual values and the predicted values, they are in a linear manner. Okay. And then we'll check the R2 score, the variance score, as well as the RMSE. Sorry, the mean squared error. So now here is what you need to know about R2 score. R2 score, higher the better. Okay, so it is between -1 to 1. You want it to be as close to 1 as possible. And mean squared error should be as low as possible. So here we are noticing that our R2 score is 0.63 and our mean squared error is 190, 1984 something. Now that is not a good value. That is not a good output. Okay. So we'll try to improve our model. So now what we'll do is we'll take time on app. Time on app has the second highest correlation. It has the second highest correlation, and at the same time we observe that it has got the second most linear looking pair plot. Okay, so you take that, we again do the split, we again do the regression, and now we find the coefficient. So now the coefficient, our equation would look something like this: y equals to 38.6 of x1 plus 62.5 of x2 minus 187. Something like this. Obviously, you can have to put this full values in, but for the sake of simplicity, I'm just taking it like this. Okay. So now if time spent on app is, let's just take this as 39, as 10 hours. This will take as 63. The membership length is 2 years minus 187. So this person is likely to spend 390 plus 126 minus 187. Okay, that would be, let me just quickly calculate. That would be 390 plus 126 minus 187. That would be 329. A person with a 2-year membership and a time spent on app as 10 hours is likely to spend $329, rupees, whatever the exchange currency they are taking. Okay. So now we have derived another equation. Now let's verify. Let's check the results. Let's take a look at the graph. Now, between this graph, the first one we got, and this graph, you can already see that the divergence, the variance has reduced. The divergence has between the actual and predicted value has been reduced. So what we can conclude here? We can conclude that we are actually on the right track. Okay. We are actually on the right track here. And then finally, we'll take our R2 score and MSC. Now, already previous one was in simple linear regression that we used. R2 score was 0.63, MSC was 1984 point something. In multiple linear regression 1, where we are taking two variables, R2 is 0.86 and mean squared error is 753. So we are already seeing a dramatic improvement in our model performance. Now, this improvement indicates that having more variables is probably going to be more useful. Okay. So now we take average session length. Okay. Now we are taking average session length as well. Now average session length had the third lowest correlation, 0.36, with yearly amount spent. Okay. So we'll add it, weak correlation, but correlation nevertheless. We'll again do our splitting. We'll again fit the linear regression model. And now again, we are getting some equation and these values have changed again. Time on app 38.6 something. The length of membership has changed. The average session length has changed. So, and the intercept value has also changed. The intercept value is minus 1000 now. Okay. So let's see the prediction. Now you can see the predictions are even more linear to each other. That means we are getting closer and closer to finding the perfect solution. Now, if we compare the results, our R squared is 0.98 and our MSC is 103.9. This is again a dramatic improvement on our model performance. Okay. So now let's try to take all four variables and see if we can make a difference to our model. So here we'll also take this time on website. Okay. It has very poor correlation, negative poor correlation. Anyhow, we'll just take it for the sake of experimentation. Okay. So again, we fit the linear regression. Let's get our equation. We've got these values, fitting it on a regression model. Okay. So here we need to add this time on website. And this would be in index position 3. And here we are going to take lm.width underscore 3. Okay. So now we have this time on website as well. And there is some change in the values, but as such, time on website is showing it has got a very little effect on our model. Okay. Now let's see if it is going to make it better. Looks very similar. Doesn't look like it has improved much or doesn't look like it has become worse. But the best way is obviously to check the R2 score and the MSC. So no improvements, I guess. Slight improvements, 0.98086, 0.98087. So slight improvements are there. But again, the improvements do not justify the amount of effort it takes to add another column. So what we can conclude here is time on app, length of membership, and average session length are all you need to predict yearly spend. All right. So we can conclude this. We can get some relation. We don't have to worry about getting time on website. Okay. So that is regression. Now what we have learned here is how to build a linear regression model, a simple linear regression, how to make a simple linear, how to make a multilinear regression model. All right. So I think that should really cover it. Yesterday we had done KNN, and if I remember correctly, in KNN we were trying to find out what was going to happen if you took 225 K neighbors. So I did that. Let me just share my screen. So here we had taken 226 as K value. Why we did it? Because we had 51,000 rows, and I just wanted to take the square root of those rows and see if it is going to improve the model performance. So it took about an hour for it to predict with 226 up to 226. And this is the mean accuracy. You can notice that there is hardly any improvement. We are stuck in 0.5 values. Okay. So again, you can notice that after a while, after the initial K values, you are not getting much improvement. Early on, the improvement is decreasing, then it is increasing, and then it is stabilizing. All right. So the best accuracy was with K as 186, and it was 59%. So that means our KNN model in this scenario was not very useful. All right. So maybe we'll try this data set with a different scenario and see if it is useful for us. But this data set, this was very useful for us. In this data set, this um, linear regression equation, this one, this linear regression equation is basically the perfect equation that describes the relationship between the input and the output variables. So now I hope that you are able to understand linear regression. Okay. So if you have any questions, you can ask now. Otherwise, we can wrap up the session.